Imagine you have a baseball. It has weight. It has substance. You can hold it in your hand. This is matter. It's the stuff everything you know is made of. The chair you're sitting on, the air you're breathing, you. All of it is matter. Now, imagine there's another baseball. It looks exactly the same. And it weighs the same, it has the same size and shape, but it's a mirror image of the first baseball in a very deep, fundamental way. It's an anti-baseball. This is antimatter. For every particle of matter that exists, there's a corresponding antiparticle. And an electron, the tiny particle that zips around atoms and powers our electronics, has an antimatter twin called a positron. It has the same mass as an electron, but it has a positive charge instead of a negative one. A proton, the heavy particle in the nucleus of an atom, has an antiproton. It has the same mass, but a negative charge instead of a positive one. So you have your baseball and your anti-baseball. On their own, they're perfectly stable. The baseball sits in your hand. The anti-baseball, if you could hold it, would sit just as calmly in your other hand. They are both real, solid things. But what happens if you bring them together? What happens when matter and antimatter collide? The answer is simple and violent. They annihilate. The word annihilate comes from Latin and it means to bring to nothing. And in a way, that's what happens. The baseball and the anti-baseball would vanish. They would cease to exist as matter. The protons and antiprotons would disappear. The electrons and positrons would disappear. All the substance, all the mass would be gone. But it doesn't just turn into nothing. That would violate one of the most fundamental laws of the universe, the conservation of energy. Energy cannot be created or destroyed, only changed from one form to another. And mass, as Einstein famously showed us, is a form of energy. A very, very concentrated form of energy. His equation, EmEc2, tells the story. Energy E equals mass m times the speed of light c squared. The speed of light is a huge number. The speed of light squared is an astronomically huge number. This means that even a tiny amount of mass is equivalent to a staggering amount of energy. When matter and antimatter collide, all of their mass is converted into pure energy with 100% efficiency. There is no more efficient process known in the universe. It is the ultimate conversion. So when the baseball and the anti-baseball touch, they don't just disappear with a quiet poof. They erupt in a blinding flash of energy. This energy takes the form of high-energy photons, which are particles of light. And specifically, they would be gamma rays, the most energetic form of light there is. It would be an explosion of unimaginable power. Let's break it down to the simplest possible interaction. An electron meets a positron. The electron has a negative charge. The positron has a positive charge. They are drawn to each other by their opposite electrical forces. When they get close enough, they spiral in towards each other, and then they annihilate. Their mass is converted entirely into energy. Usually, this creates two gamma-ray photons that fly off in opposite directions. They fly off in opposite directions to conserve momentum. The universe likes to keep its books balanced. Before the collision, the electron and positron system had a certain momentum. After the collision, the total momentum must be the same. Two photons flying off in opposite directions balances everything out perfectly. That's the clean, simple version, an electron and a positron. But what about more complex things, like a proton and an antiproton? This is where it gets a little messier. A proton isn't a fundamental particle like an electron is. It's made of smaller particles called quarks. An antiproton is made of antiquarks. When a proton and an antiproton collide, it's not just a clean conversion into two photons. The quarks and antiquarks inside them annihilate, creating a chaotic burst of new, unstable particles. These particles are called mesons, like pions and kaons. These newborn particles don't live for long. They decay almost instantly into other things, like muons, neutrinos, and more photons. So, instead of a clean flash of two gamma rays, the annihilation of a proton and antiproton is a shower of various particles and radiation. It's still a complete conversion of mass to energy, but the energy is released in a more complicated multi-stage process. Now let's go back to our baseball and anti-baseball. An entire atom of hydrogen is made of one proton and one electron. An atom of antihydrogen is made of one antiproton and one positron. If you brought these two atoms together, the electron and positron would likely find each other first and annihilate, releasing their two gamma rays. A split second later, the now bare proton and antiproton would collide, annihilating into that messy shower of other particles. For something as big as a baseball, which contains trillions upon trillions of atoms, a collision with an anti-baseball would be a cataclysm. Every single particle would meet its antiparticle counterpart. Every last bit of mass from both objects would be converted into a storm of gamma rays, neutrinos, and other exotic particles. The release of energy would be immense, far greater than any chemical or nuclear explosion we have ever created. A single gram of antimatter annihilating with a gram of matter would release roughly the same energy as the atomic bomb dropped on Hiroshima. A baseball's worth would be many, many times more powerful than that, so why does this happen? Why is annihilation the inevitable result? It goes back to the idea of a mirror image. Particles have properties beyond just mass and charge. They have quantum numbers, which are like little internal labels. For example, an electron has something called a lepton number of plus. A positron has a lepton number of 1. When they meet, their total lepton number is plun plus 1, which equals 0. A proton has a baryon number of plun. An antiproton has a baryon number of 1. When they meet, their total baryon number is 0. The universe demands that these quantum numbers, these fundamental labels, be conserved. When a particle and its antiparticle meet, their properties are perfectly opposite. They cancel each other out completely. Charge cancels, lepton number cancels, baryon number cancels. It's like adding a number and its negative counterpart. You get 0. The only things left that must be conserved are energy and momentum. The only way for the universe to do this, to get rid of the particles while keeping the energy and momentum, is to convert the mass into pure energy in the form of photons or other particles that carry that energy and momentum away. Annihilation isn't just a random event, it's the physical embodiment of cancellation. This all sounds like science fiction, but antimatter is very real. It's just incredibly rare. The universe around us, as far as we can see, is made almost entirely of matter. So where do we even find antimatter? It is created naturally in some very high energy events. For example, some radioactive elements undergo a process called beta plus decay. In this process, a proton inside an atom's nucleus turns into a neutron, and in doing so, it spits out a positron. This is a natural, albeit tiny, source of antimatter. High-energy cosmic rays, which are particles zipping through space, can also slam into our atmosphere and create tiny particle-antiparticle pairs out of pure energy. This is EM82 running in reverse. If you have enough energy concentrated in one place, you can create a particle and its antiparticle. You can literally make something out of nothing but energy. This happens around violent cosmic objects too, like black holes and neutron stars, where energies are extreme. But these natural sources produce antimatter in tiny, fleeting amounts. The positrons created almost immediately find an electron to annihilate with, releasing a little puff of gamma rays. To study antimatter, we have to make it ourselves. We do this in massive machines called particle accelerators. Places like CERN in Europe are essentially antimatter factories. The basic idea is to take a beam of particles, like protons, and accelerate them to nearly the speed of light. Then you smash that high-speed beam into a target, usually a block of metal. The collision is so incredibly energetic that some of that energy is converted into new particles. And whenever you create matter from energy, you must also create an equal amount of antimatter to keep the books balanced. So, the debris from these collisions contains a spray of all sorts of particles, including antiprotons and positrons. Creating antimatter is one thing, catching it and holding on to it is another. It's an incredibly difficult problem. You can't just put it in a bottle. The walls of the bottle are made of matter. The instant the antimatter touched the walls, it would annihilate. Even the air in the bottle is matter. So, you have to store it in a perfect vacuum, and you have to hold it there without it touching anything. Scientists do this using powerful and complex magnetic and electric fields. They create a sort of magnetic bottle, or trap. Since antiparticles have charge, like the antiproton's negative charge, you can use magnetic fields to push and pull them, guiding them into the center of a chamber and holding them there, suspended in a vacuum, never touching the sides. A place like CERN, they have managed to create and trap antiprotons. They've even gone a step further and combined antiprotons with positrons to create the first complete atoms of antihydrogen. But the process is unbelievably inefficient. For every million high-energy collisions, you might get only one usable antiproton. The amount of energy you have to put into the accelerator to create a tiny speck of antimatter is vastly more than the energy you would get back from annihilating it. We are talking about making antimatter literally one atom at a time. The total amount of antimatter ever created and trapped by humans is minuscule, far, far less than a gram. It would not be enough to power a light bulb for even a fraction of a second. The cost is also astronomical. Producing just 1 gram of antimatter with our current technology would cost more money than has ever existed in the entire global economy. Despite its rarity and cost, antimatter does have a very important practical application right now, and it's in the world of medicine. It's used in a technique called positron emission tomography, or a PET scan. Here's how it works. A patient is injected with a special sugar molecule that has a radioactive atom attached to it. This radioactive atom is one that decays by spitting out positrons antimatter. The sugar is carried through the bloodstream and is absorbed by cells in the body. Cancer cells, for example, are often more metabolically active than normal cells, so they gobble up more of this sugar. As the radioactive atoms decay, they release positrons into the patient's body. These positrons don't travel very far. Within a millimeter or two, they bump into an electron from a nearby atom, and then annihilation. The positron and electron disappear and create two gamma-ray photons that fly off in exactly opposite directions. The PET scanner is a ring of detectors around the patient. When two detectors on opposite sides of the ring detect a gamma ray at the exact same instant, the machine knows that an annihilation event happens somewhere on the straight line connecting those two detectors. By recording millions of these events from all angles, a computer can reconstruct a 3D image showing exactly where the radioactive sugar has accumulated. This allows doctors to see tumors or look at brain activity with incredible detail. It is a life-saving technology, and it works because of the fundamental physics of matter-antimatter annihilation. Beyond PET scans, the incredible energy density of antimatter makes it a tantalizing subject for future technologies, especially in the realm of science fiction. The most common idea is using antimatter as a fuel source. As we discussed, matter-antimatter annihilation is 100% efficient at converting mass to energy. For comparison, burning gasoline is a chemical reaction that is less than 1/1000th of 1% efficient. It only rearranges electrons in molecules. The mass is barely changed. Nuclear fission, which powers our nuclear reactors, is about 0.1% efficient. It splits heavy atoms and converts a tiny fraction of their mass into energy. Nuclear fusion, the process that powers the sun, is about 0.7% efficient. It fuses light atoms together and converts a slightly larger fraction of mass into energy. Antimatter is in a league of its own. A fuel source that is 100% efficient would be the ultimate game changer. A few milligrams could power a city. A few kilograms could power a starship. This leads to the concept of an antimatter rocket. A conventional rocket works by burning chemical fuel and throwing the hot gas out the back. It's inefficient. You need huge amounts of fuel for a small payload. An antimatter rocket would be different. The idea would be to take a small amount of antimatter and annihilate it with a small amount of matter. This would create a blast of high-energy particles and photons. You would then use a magnetic nozzle to direct this blast out the back of the ship. Because the energy release is so immense, the particles would be ejected at close to the speed of light. This would provide a much more powerful and efficient thrust than any chemical rocket. A ship powered by an antimatter drive could theoretically reach other stars within a human lifetime, something that is completely impossible with our current technology. Of course, the challenges are monumental. First, you have to produce the antimatter. We would need a technology thousands or millions of times more efficient than what we have today, just to produce the grams or kilograms needed for a single mission. Then you have to store it safely for years on a spaceship. A failure in the magnetic containment system would be catastrophic. The antimatter would touch the walls of its container, and the entire ship would be destroyed in a flash of gamma rays. Finally, you have to control the annihilation reaction. You would need to feed tiny, precise amounts of matter and antimatter into a reaction chamber to generate a steady, controlled thrust, not just a single, violent explosion. These are engineering problems so far beyond our current capabilities that they remain firmly in the realm of science fiction. There's also a darker side to this potential. If antimatter can be used as a fuel, it can also be used as a weapon. An antimatter bomb would be the most powerful weapon theoretically possible. As we said, a gram of antimatter would be equivalent to a major nuclear weapon. There would be no nuclear fallout in the traditional sense, as no heavy atoms are being split. But the blast itself would be devastating, and the intense burst of gamma radiation would be instantly lethal for miles around. Fortunately, given the absurd cost and difficulty of producing antimatter, an antimatter weapon is not a practical concern. It's a terrifying concept, but not a realistic threat with today's technology, or any technology we can foresee in the near future. All of this talk about antimatter, about its creation and its spectacular annihilation, leads to one of the biggest and most profound mysteries in all of physics. If the laws of physics are symmetrical, and if energy creates matter and antimatter in equal pairs, then the Big Bang should have created an equal amount of matter and antimatter. In the very first moments of the universe, the cosmos was an incredibly hot, dense soup of energy. As it expanded and cooled, that energy should have condensed into particles. For every quark, an antiquark should have been born. For every electron, a positron. The early universe should have been a perfect 50-50 mix of matter and antimatter. So, what should have happened next? As the universe continued to cool, all that matter and antimatter should have found each other. They should have annihilated. The entire universe should have turned into a sea of photons, a universe filled with light and nothing else. There would be no galaxies, no stars, no planets, and no people. The substance of the universe should have canceled itself out moments after it was born. But that's not what happened. We are here. The world around us is made of matter. The solar system is matter. Our galaxy, the Milky Way, is matter. When we look out at other galaxies, they all appear to be made of matter too. If there were huge galaxies made of antimatter out there, we would see a clear signature. At the boundary where an antimatter galaxy meets a matter galaxy, there would be a constant, massive scale annihilation happening. This would produce a very specific background of gamma rays that we just don't see. So, the great mystery is this. Where did all the antimatter go? Or, to put it another way, why is there any matter left at all? Somehow, in the early universe, the perfect symmetry was broken. For some reason, for every billion pairs of antimatter and matter particles that were created, there was one extra matter particle. Just a tiny imbalance, a billion pairs annihilated, creating the sea of photons that we now see as the cosmic microwave background radiation, the leftover heat from the Big Bang. And that one extra particle in a billion was left over. That tiny remnant, that cosmic leftover, is what makes up everything we see today. Every star, every galaxy, every atom in your body is a survivor of that great annihilation. Physicists are still struggling to understand how this asymmetry happened. There are theories, of course. They involve subtle differences in the way certain exotic particles and antiparticles decay, a phenomenon known as CP violation. The idea is that maybe matter and antimatter are not perfect mirror images after all. Maybe there's a tiny, subtle flaw in the mirror. Over the immense number of interactions in the early universe, this tiny flaw could have added up, leaving behind a small surplus of matter. But so far, the subtle differences we have found in our experiments are not nearly enough to explain the vast cosmic imbalance we see. The mystery remains, so when matter and antimatter collide, the result is the most complete and energetic transformation possible in our universe. It is a process of total annihilation, a conversion of substance into pure energy, governed by the deepest laws of physics. It happens in our hospitals to save lives, it fuels the dreams of starships, and its ghost lingers in the very structure of the cosmos. It reminds us that for all we have learned about the universe, there are still fundamental questions we cannot yet answer. The simple fact that we exist to ask the question is proof that in the first moments of time, something profound and mysterious happened to tip the scales, ensuring that the universe would be filled with substance instead of just light. The collision of matter and antimatter is not just a physical process, it is a key to understanding why there is a universe at all.